February 27th, 1944, near Anzio, Italy. The Panther's 75mm round struck the Sherman at 800 meters, penetrating clean through the sponson where American doctrine said ammunition was stored. Oberfeldwebel Klaus Werner watched through his gunner's optics, already traversing toward the next target. In 3 seconds, maybe 5, that Sherman would erupt in flames. The crew would burn, or if lucky, bail out with third-degree burns covering half their bodies. Werner had seen it dozens of times, since Tunisia. Hit a Sherman in the sponson, watch it cook off, move to the next target. But the flames never came. The Sherman's turret continued traversing, its barrel swinging toward Werner's Panther with deliberate purpose. The American tank's engine still growled. Smoke poured from the penetration hole, but no fire. Werner's loader, already reaching for another round, froze mid-motion. That was impossible. Every intelligence briefing, every combat report, every technical manual said American tanks burned when you hit their ammunition storage. The Panther's commander screamed into the intercom to fire again, but the Sherman fired first. Its 76mm round punched through the Panther's turret ring, killing 3 of the 5-man crew instantly. What Oberfeldwebel Werner witnessed in those confused seconds was a revolution in armoured warfare that German intelligence had completely missed. The M4A 376W Sherman that had just killed his crew belonged to the 760th Tank Battalion. Every round of its 71-round main gun ammunition load sat surrounded by liquid-filled, double-walled containers that prevented the catastrophic ammunition fires German gunners had relied upon since 1942. This modification, present in every Sherman tank produced after January 1944, had reduced fire probability after penetration from 60 to 80% down to 10 to 15%. Across the Anzio beachhead that morning, American armoured units were fighting with these improved Shermans. Not one German intelligence report, not a single briefing from Wehrmacht technical branches, not even rumours from the Eastern Front had warned Panzer crews that their primary tactical assumption about American armour had become lethally obsolete. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The transformation that would save thousands of American lives and help win World War II had begun in the aftermath of catastrophic defeat. February 14, 1943. Kasserine Pass, Tunisia. American armour burned across the valley floor. M4 Shermans transformed into steel crematoriums by German 88mm guns, firing from concealed positions in the hills. Combat Command A of the 1st Armoured Division had entered the pass with 98 medium tanks. Within 6 hours, 44 lay destroyed, most consumed by ammunition fires that killed entire crews before they could escape. The British Operational Research Section, conducting systematic analysis of knocked-out tanks across North Africa, documented brutal statistics. 65% of destroyed Shermans burned completely, leaving nothing but charred hulls and the remains of their crews. American studies reviewing the same battlefield evidence showed even worse figures in some engagements, approaching 80% burn rates for penetrated tanks. The problem wasn't the gasoline engine, despite persistent myths that would survive into the 21st century. The Ordnance Department's Tank Automotive Center at Detroit Arsenal analyzed every knocked-out Sherman recovered from North African battlefields. Their metallurgical teams examined burn patterns, interviewed surviving crew members, and reconstructed the sequence of events in hundreds of tank destructions. Their conclusion, documented in classified reports distributed to senior Army leadership in March 1943, was unambiguous and terrifying. Ammunition propellant, not fuel, caused nearly 90% of catastrophic fires. The 75mm rounds, stored in racks throughout the Sherman's fighting compartment, became instantaneous incendiaries when struck by armor-piercing shot or fragments from penetrating rounds. The physics were simple and deadly. Each 75mm round contained approximately 1 pound of M1 propellant, a nitrocellulose-based compound that ignited at relatively low temperatures. A Sherman carried 90 to 100 rounds depending on variant. When an armor-piercing round penetrated the hull, it created a shower of white-hot metal fragments traveling at supersonic speeds. These fragments, some still burning at over 1,000 degrees Fahrenheit, would strike ammunition racks positioned in the sponsons above the tracks, easily accessible for the loader but catastrophically vulnerable to enemy fire. Once propellant ignited, the fire spread through interconnected ammunition storage areas within seconds. Temperatures inside the fighting compartment reached 2,000 degrees Fahrenheit in less than 30 seconds. Crew members had perhaps 10 to 15 seconds to escape before heat and toxic fumes made survival impossible. The Ordnance Department faced a crisis that threatened the entire American armored warfare doctrine. By spring 1943, American industry had tooled up to produce Sherman tanks at unprecedented rates. Contracts had been issued to 11 different manufacturers, from locomotive works to car companies, creating a distributed production network that could sustain massive output even under enemy attack. But quantity meant nothing if every tank became a death trap the moment enemy rounds penetrated its armor. Senior Army leadership demanded solutions, and they demanded them immediately. The answer emerged from an unexpected source during a tank board meeting at Aberdeen Proving Ground in November 1943. Dr. James Hamilton, a chemical engineer from DuPont, attending the meeting as a technical consultant on propellant storage, listened to ordnance officers describe the ammunition fire problem in increasingly desperate terms. Hamilton had spent 15 years working on industrial safety systems for chemical plants, handling volatile materials. He understood that the fastest way to prevent combustion wasn't removing oxygen, an impossible task in a combat vehicle, but removing heat through immediate cooling of any ignition source. Hamilton's initial suggestion seemed absurd to the military officers present. Surround ammunition with water, create sealed, double-walled containers with liquid filling the gap between walls. When a penetrating round struck the ammunition bin, the liquid would flood out, immediately cooling any hot fragments and soaking exposed propellant before it could reach ignition temperature. The objections came fast. Water would freeze in winter. Water would corrode brass cartridge cases. Water would add unacceptable weight. Water-filled compartments would slosh during movement, affecting vehicle stability. The concept violated every principle of ammunition storage the Ordnance Department had developed over decades. But Hamilton persisted, pointing to industrial applications where similar principles prevented fires in chemical facilities. The key wasn't just flooding the area with water after a fire started. The key was preventing ignition in the first place, by ensuring that any potential ignition source immediately encountered cooling liquid before it could raise propellant temperature to combustion point. The physics were straightforward. Nitrocellulose propellant required sustained temperature above approximately 360 degrees Fahrenheit to ignite reliably. A shower of liquid at ambient temperature, even cold liquid from winter conditions, would absorb heat faster than fragments could raise propellant temperature, preventing combustion entirely. The Army established a rushed development program at Aberdeen Proving Ground, starting December 1943. Engineers built mock-up ammunition containers with double walls, testing various configurations and liquid types. They fired captured German 75mm and 88mm guns at these containers from combat ranges, measuring temperature, propellant ignition rates, and liquid distribution patterns. The early tests used simple water between double walls. The results exceeded even optimistic projections. Dry ammunition storage detonated in 73% of hits when fragments struck stored rounds. Water-surrounded ammunition ignited in only 15% of identical tests. When ignition did occur, the water prevented fire spread, containing combustion to the specific round struck rather than cascading through adjacent ammunition. But water alone presented problems that became apparent during extended testing. In sub-freezing conditions, water froze solid, eliminating all protective effect. Even above freezing, standing water promoted corrosion on brass cartridge cases, potentially causing misfires or dangerous pressure variations during firing. Bacterial growth in stagnant water created additional contamination risks. The development team needed a liquid that remained fluid in extreme cold, prevented corrosion, inhibited bacterial growth, and maintained or improved fire suppression effectiveness compared to pure water. Chemical engineers experimented with various additives through January and February 1944. Ethylene glycol, the standard antifreeze used in vehicle engines, solved the freezing problem but accelerated corrosion on brass, unacceptable for ammunition storage. Glycerol-based solutions prevented freezing and reduced corrosion but proved too viscous, not flooding quickly enough when containers were penetrated. The breakthrough came with a compound called Amudamp, specifically ethyl sodium potassium phosphate, with proprietary rust inhibitors and biocides, developed by DuPont for industrial applications. This mixture remained liquid to -40 degrees Fahrenheit, actively prevented corrosion through pH buffering, inhibited bacterial growth through biocidal additives, and actually improved fire suppression compared to pure water through chemical heat absorption properties, exceeding water's already excellent thermal capacity. By late February 1944, the Army had a working solution ready for production implementation. Each ammunition bin would consist of precision-manufactured double-walled containers with 1.5-inch gaps between inner and outer shells. These gaps would contain approximately half a gallon of Amudamp solution per 10-round cell. The complete system for a 76mm armed Sherman required 36.6 gallons of liquid protecting 71 rounds. For 75mm variants, 37.1 gallons protected 90 rounds stored in hull floor positions, plus 4 ready rounds in the turret. The modification required complete redesign of Sherman hull floors. Ammunition that had been stored in vulnerable sponson positions above the tracks since initial production now moved to protected positions in the hull floor beneath the turret basket. This placement offered multiple advantages beyond just adding liquid protection. Hull floor positions sat lower in the vehicle, behind thicker armor, and further from typical impact points. The ammunition sat beneath the crew rather than beside them, meaning even if fire occurred, it would take longer to reach the fighting compartment. Most importantly, moving ammunition out of the sponsons eliminated the most vulnerable storage location, where German gunnery doctrine specifically trained crews to target. But the redesign presented enormous manufacturing challenges. Press Steel Car Company in Pennsylvania, one of the primary Sherman manufacturers, had to create entirely new hull stamping dies, modify welding jigs, and redesign assembly sequences. The turret basket, the rotating floor that allowed crew members to move while the turret traversed, had to become partial rather than complete, with openings allowing access to hull floor ammunition. This meant redesigning the entire turret traverse mechanism, rerouting hydraulic lines, electrical cables, and control linkages around the new ammunition positions. The changes touched virtually every aspect of Sherman production, from raw steel stamping through final assembly. American industry accomplished this transformation with speed that would have seemed impossible to European manufacturers accustomed to years-long development cycles. Press Steel Car Company completed its retooling and produced the first M4A 176W Sherman, the W designation standing for wet stowage, on January 3, 1944. Fisher Tank Arsenal in Grand Blanc, Michigan, the largest single Sherman production facility, transitioned from M4A2 to M4A3 production while simultaneously incorporating wet stowage modifications without stopping its assembly lines. Between February 1944 and March 1945, Fisher alone produced 3,711 M4A376W tanks, each one incorporating the life-saving modification. The statistical impact of this engineering change would prove devastating to German tactical planning, though German intelligence would never recognize what had occurred. A Sherman battalion equipped with older dry storage tanks suffering 30 penetrating hits in combat could expect to lose 18 to 24 tanks to fire with 60 to 80% burn rates. Those same 30 penetrations against wet storage, Shermans would cause fires in only 3 to 5 tanks, leaving 25 to 27 vehicles repairable and returnable to service. a tank battalion that should have been combat ineffective after a single major engagement, instead maintained operational strength, able to continue fighting while replacement vehicles and repaired tanks reinforced its ranks. This invisible multiplication of American armoured strength would confound German planning at every level for the next 15 months. Testing at Aberdeen Proving Ground validated the system's effectiveness under the most extreme conditions engineers could devise. They fired 88mm armour-piercing rounds at wet stowage bins from point-blank range, creating maximum fragment generation. They tested penetrations from multiple angles, from direct hits perpendicular to armour, through glancing blows that created maximum fragment spray inside the fighting compartment. They deliberately struck ammunition bins after draining liquid, testing whether even empty. Double-walled containers offered any protection compared to original single-wall storage. Every test confirmed the same result. Wet stowage reduced fire probability by 75 to 85% compared to dry storage under identical conditions. The Army classified these test films secret until 1963, keeping detailed footage of the dramatic differences from public view for nearly 2 decades after the war. The films showed dry ammunition erupting in pillars of orange flame, consuming entire mock-up tank interiors in seconds. The same penetrations against wet storage produced small puffs of smoke, quickly extinguished as liquid flooded out, soaking surrounding areas. In some tests, wet storage prevented ignition entirely, with liquid cooling fragments before they could raise propellant temperature to combustion point. The visual evidence was undeniable, overwhelming, and immediately convinced skeptical ordnance officers that the modification warranted immediate fleet-wide implementation. By April 1944, 130 M4A 176W Shermans had arrived in England, assigned to the 2nd and 3rd Armoured Divisions preparing for the invasion of France. Each division received 52 of these tanks, though initial deployment was delayed by concerns about crew training on the new 76mm gun and ammunition supply logistics for the higher velocity round. These improved Shermans would miss the D-Day landings on June 6th, but they would enter combat barely 6 weeks later during Operation Cobra, the breakout from Normandy that would shatter German defensive lines and send American armour racing across France. German intelligence, meanwhile, continued operating with analysis based on Sherman tanks captured in Tunisia during 1943, more than a year before wet stowage entered production. At Kummersdorf Proving Ground outside Berlin, German technical specialists had conducted exhaustive evaluation of M4A1, Shermans captured intact during the battles around Kasserine Pass. The resulting technical intelligence bulletins, distributed throughout Wehrmacht Panzer units, contained detailed drawings of ammunition rack placement in sponsons above track level, with specific recommendations to target these areas for maximum effect. German gunnery schools from Putlos to Paderborn taught students to aim for Sherman sponsons as the most reliable method of achieving catastrophic kills. Range cards issued to anti-tank units highlighted these vulnerable areas in red. The tactical doctrine became so thoroughly embedded that it would persist through war's end, even as the vulnerability it targeted ceased to exist. The timing proved catastrophic for German forces defending France. Their comprehensive Sherman analysis had concluded just as American factories began producing fundamentally different vehicles. Every subsequent intelligence update referenced the older Kummersdorf evaluation as definitive. When frontline units began reporting unusual Sherman survivability rates in summer 1944, staff officers dismissed these observations as exaggerations from combat-stressed troops who couldn't accurately assess combat results. The systematic intelligence failure that resulted would cost Germany dearly in the battles to come, as Panzer commanders planned operations based on obsolete assumptions about American tank vulnerability that no longer reflected battlefield reality. Operation Cobra commenced at 09:38 hours on July 25, 1944, with the heaviest aerial bombardment in tactical support history. 1,500 heavy bombers from 8th Air Force dropped 4,000 tons of high explosives on a rectangular target area 5 miles wide and 1.5 miles deep near Saint-Lô, Normandy. As smoke cleared from the carpet bombing, American armor surged forward through the gap. Leading elements included the 2nd and 3rd Armored Divisions, equipped with the first wet-stowage Shermans to see combat in the European theatre. Panzer Division, positioned directly in the bombardment zone, had been devastated. Of its 183 tanks and assault guns operational on July 24th, only 47 remained combat-capable after the bombing. Those survivors withdrew to prepared defensive positions, attempting to create strongpoints that would channel American armor into killing zones where German guns could engage at favorable ranges. Panzer's Panthers, positioned in concealed positions along tree lines and in Norman villages, achieved multiple penetrating hits on advancing Shermans during the first hours of combat. German after-action reports, captured when Panzer's headquarters was overrun 3 days later, reflected growing confusion about American tank resilience. Panther gunners were achieving clean penetrations on Shermans at 600 to 800 meters, well within effective range of their 75mm Kia WK-42 guns. Yet many targets continued fighting or withdrew under their own power rather than burning as doctrine said they should. Panzer commanders, calculating American strength based on observed destructions, consistently underestimated the number of operational American tanks they faced. The 2nd Armored Division, which should have been combat ineffective after the first day's fighting according to German calculations based on observed hits, instead maintained offensive pressure throughout the week. What German crews didn't know was that they had encountered M4A 376W and M4A 176W Shermans from the 67th and 33rd Armoured Regiments. Of the tanks German gunners believed destroyed, many would return to action within 24 to 48 hours after field repairs by maintenance battalions. Those that did burn had typically been struck in the engine compartment, where gasoline fires remained as lethal as ever, or had suffered multiple penetrations that overwhelmed even wet stowage protection. But the ammunition fires that should have consumed 60 to 80% of penetrated tanks simply weren't occurring at expected rates. The engineering behind the system represented exceptional wartime innovation compressed into remarkably brief development time. Each storage bin consisted of precisely manufactured double-walled containers fabricated from welded steel plate. The inner wall, made from 1/8-inch steel plate, provided structural support and protected ammunition from minor impacts during vehicle operation. The outer wall, also 1/8-inch plate, formed the exterior of the container. Between these walls ran a precise 1.5-inch gap filled with Amudamp solution. This gap dimension proved critical. Too narrow and insufficient liquid volume would be available to cool fragments and soak propellant. Too wide, and the liquid would add excessive weight while potentially sloshing violently during vehicle movement. Engineers calculated that half a gallon of liquid per 10-round cell provided optimal balance between protection and practical considerations. Each cell held 10 75mm or 76mm rounds in individual compartments that prevented round-to-round contact. This separation meant that even if one round ignited despite the liquid protection, physical barriers plus liquid flooding would prevent fire spread to adjacent ammunition. The system incorporated clever engineering details that made field maintenance practical. Each bin included inspection ports, allowing crews to check liquid levels without disassembling components. Drain plugs at the bottom allowed complete liquid removal for maintenance, or when operating in Arctic conditions where even Amudamp's -40°F freeze point might be exceeded. Fill ports at the top, sealed with rubber gaskets and threaded. Caps allowed replenishment of liquid that had slowly leaked through welds or been lost through combat damage. The Army's Ordnance Department issued specific maintenance procedures, requiring crews to check liquid levels weekly and top off bins as needed. Depot-level maintenance facilities received bulk shipments of Amudamp solution in 55-gallon drums, with distribution networks ensuring supplies reached frontline units. The entire logistics chain, from DuPont chemical plants in Delaware through Atlantic shipping to depot facilities in England and France, operated smoothly despite the complexity of supplying a specialized industrial chemical to combat zones. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. At Kummersdorf, German technical intelligence continued analyzing American equipment using specimens that predated wet stowage by more than a year. The detailed evaluation of early M4A1 tanks from 1st Armored Division remained the authoritative reference for all Wehrmacht intelligence on Sherman capabilities. Additional Shermans captured in Italy during spring and summer 1944 were briefly examined, but not subjected to the comprehensive testing that might have revealed the fundamental changes in ammunition storage. German intelligence officers, operating under severe resource constraints as Allied bombing disrupted every aspect of German military operations, prioritized immediate tactical intelligence over systematic technical evaluation. The few technical specialists still working at Kummersdorf focused their limited resources on analyzing new American weapons like the Pershing heavy tank, captured in small numbers in early 1945, rather than re-examining the Sherman, which intelligence believed was thoroughly understood from previous studies. This analytical complacency, combined with organizational dysfunction across German intelligence services and the simple fact that wet stowage looked identical from outside the tank, created an intelligence blind spot that would persist through the war's end. The bocage country of Normandy became an inadvertent proving ground for wet stowage effectiveness under the worst possible combat conditions for American armor. The hedgerow terrain, where centuries-old earthen walls topped with dense vegetation divided the Norman countryside into countless small fields, forced combat at ranges where German guns easily penetrated Sherman armor. American doctrine emphasized rapid movement and combined arms coordination, but the bocage negated mobility advantages, channeling armor onto predictable routes where German anti-tank guns waited in ambush. Yet despite these tactical disadvantages, American tank losses proved surprisingly recoverable. Third Army's maintenance battalions reported recovering and repairing 67% of knocked-out Shermans during Operation Cobra and the subsequent breakout battles. Of tanks that would have been total fire losses with dry storage, approximately 70% returned to service with the new protection. Maintenance crews could replace damaged armor plate, swap out penetrated final drives, install replacement transmissions, even replace entire turrets on tanks that had suffered turret ring penetrations. But they couldn't resurrect tanks that had burned to charred hulls with fused components and heat-warped hulls. Wet stowage transformed potentially total losses into repairable battle damage. This invisible multiplication of American tank strength confounded German planning at every operational level. Corps and Army-level intelligence staffs, tracking American armor strength through daily situation reports, consistently underestimated American capabilities because their calculation models remained based on 1943 data, showing 60 to 80% of penetrated tanks becoming permanent losses. When field units reported Sherman tanks bearing specific markings or serial numbers that intelligence had listed as destroyed days earlier, staff officers attributed this to faulty identification, rather than recognizing that fundamental assumptions about American tank vulnerability no longer held true. Major General Maurice Rose's 3rd Armored Division spearheaded Operation Cobra's exploitation phase with approximately 200 improved Shermans in its 3 tank battalions. In 7 days of intense combat from July 25th through August 1st, the division advanced 100 miles, fought dozens of engagements against German armor and anti-tank guns, and maintained operational momentum despite German counterattacks specifically designed to destroy American armored spearheads. German intelligence calculated that 3rd Armored should have required complete reconstitution after this week of fighting, with tank losses requiring weeks of replacement vehicle delivery, and crew training before the division could resume offensive operations. Instead, 3rd Armored continued attacking with barely diminished strength. Maintenance battalions, working around the clock in field workshops just behind the front lines, repaired and returned to service tanks that German gunners believed destroyed. Crews who had bailed out of penetrated tanks after extinguishing small fires or simply buttoning up and withdrawing under their own power were reunited with their repaired vehicles within days. The division's combat power regenerated faster than German staff officers believed possible, leading to persistent German overestimation of American reinforcement rates and underestimation of wet-stowage's impact on operational availability. The German response to Operation Cobra's success, Operation Lüttich, launched August 7th with 5 Panzer divisions, aimed at cutting off American spearheads by driving to the coast at Avranches. German planning assumed American armored units would be exhausted and depleted after their rapid advance. Intelligence estimates calculated American tank strength at roughly 60% of actual available combat power, missing entirely the hundreds of repaired and returned Shermans that wet-stowage modification had saved from permanent destruction. The plan required German armor to advance 30 miles through American-held territory, destroy or scatter American units encountered during the advance, and reach the coast before American reinforcements could seal the corridor. Success depended fundamentally on German intelligence, accurately assessing American strength and correctly estimating how quickly American units could recover from the week of intense combat that had preceded the counteroffensive. German commanders believed they faced weakened American units with limited reserves. They were wrong on both counts. The 30th Infantry Division's stand at Mortain, supported by tank battalions equipped with wet-stowage Shermans, shattered German offensive power over 6 days of intense combat. The 743rd Tank Battalion, attached to 30th Division, absorbed repeated attacks by SS and Wehrmacht Panzer units attempting to break through American defensive positions. Despite suffering numerous penetrations from German 75mm and 88mm guns, the battalion maintained cohesion and combat effectiveness throughout the battle. Tank crews who had been penetrated but not burned simply withdrew to covered positions, assessed damage, and either continued fighting if their weapons remained functional or withdrew for field repairs. Maintenance platoons worked continuously in forward areas, conducting emergency repairs on damaged tanks and returning them to combat within hours, rather than evacuating them to rear area depots. This rapid regeneration of combat power, made possible because tanks that should have burned instead suffered repairable damage, allowed American defensive lines to hold against attacks that should have achieved breakthrough, according to German planning assumptions. When Operation Lüttich collapsed after 6 days with catastrophic German tank losses exceeding 400 destroyed or abandoned vehicles, German commanders struggled to understand how American armor strength had proven so resilient. After-action reports blamed tactical failures, inadequate air cover, insufficient fuel supplies, anything except the fundamental intelligence failure regarding American tank survivability that had undermined planning from the start. The Battle of Aracourt in September 1944 provided military historians with the clearest possible demonstration of wet-stowage's operational impact. When the 113th Panzer Brigade attacked American positions near Aracourt on September 19th, they expected to achieve tactical surprise against supposedly weakened American forces. 4th Armored Division, which had spearheaded Third Army's advance across France during August, should have been significantly depleted after a month of nearly continuous combat. German intelligence estimated 4th Armored at roughly 50% strength based on observed tank losses during the preceding weeks. The initial German attack achieved numerous hits on 4th Armoured's Shermans, Panthers and Panzer IVs from 113th. Panzer Brigade reported multiple penetrations at favourable ranges during the first day's fighting. But the American response defied expectations. Instead of withdrawing with heavy losses as German planning anticipated, 4th Armoured counterattacked with unexpected strength on September 20th, destroying German armour at devastating rates through superior gunnery, better tactical coordination, and numerical advantage German intelligence hadn't known existed. The statistics from Aracourt battles tell the story with brutal clarity. 4th Armoured Division suffered 151 Sherman losses during the week-long series of engagements. Of these, only 41 were complete write-offs requiring replacement vehicles from depots. The remaining 110 tanks were repaired and returned to service by 4th Armoured's Maintenance Battalion, most within 1 week of being knocked out. German intelligence, counting all 151 as permanent losses according to their calculation models, determined that 4th Armoured should have been combat ineffective, requiring weeks of reconstitution. Instead, the division maintained offensive operations throughout, actually increasing its operational tank strength by the battle's end as repaired vehicles returned faster than new combat losses accumulated. General George Patton, initially skeptical about 76mm armed Shermans due to concerns about ammunition supply logistics, reversed his position completely after Aracourt. 3rd Army subsequently accepted only 76mm armed wet-stowage variants for replacement vehicles, recognizing that improved firepower, combined with dramatically enhanced survivability, created superior combat capability compared to earlier Sherman models. Patton's staff calculated that wet stowage effectively multiplied American armored strength by factor of 1.5 to 1.7 simply by keeping more tanks operational after combat damage, equivalent to adding entire additional tank battalions without actually shipping more vehicles across the Atlantic. As autumn 1944 progressed, second generation improved, Shermans incorporating additional refinements entered combat. The M4A3E8, nicknamed the Easy 8 by crews who appreciated its handling characteristics, combined wet stowage with improved suspension, providing better cross-country mobility despite the ammunition system's 900 pounds of added weight. Wider tracks distributed ground pressure more effectively, reducing bogging in mud that plagued earlier Shermans during autumn rains. These tanks began reaching frontline units in October 1944, with initial deliveries going to divisions that had suffered heaviest casualties during summer fighting. The specialized assault variant, the M4A3E2 Jumbo, incorporated wet stowage from initial production starting June 1944, with frontal armor reaching 4 inches and turret armor up to 6 inches, substantially thicker than standard Shermans. The Jumbo could absorb tremendous punishment from German anti-tank guns that would penetrate ordinary Shermans. Combined with ammunition fire protection, these tanks achieved survival rates that bewildered German observers who watched Jumbos absorb multiple hits and continue fighting. By November 1944, 1st Army fielded 105 M4A3E2s, distributed across various tank battalions assigned to infantry divisions. 3rd Army had 90 Jumbos concentrated in 6 separate tank battalions, doctrine called for, using Jumbos as spearhead vehicles, leading attacks on fortified positions where their superior armor protection would allow them to absorb fire while supporting Shermans engaged from protected positions. In practice, Jumbos became battalion commanders' tanks, regimental mobile reserves, and specialized assault vehicles for the most dangerous missions where ordinary Shermans would have suffered catastrophic losses. Operation Wacht am Rhein, Germany's last desperate offensive in the West, better known as the Battle of the Bulge, launched December 16, 1944, based fundamentally on flawed intelligence about American armored capabilities. German planning assumed American tank losses would follow patterns established during 1943 fighting in North Africa and Italy. The offensive's success depended on rapid destruction of American armored reserves in Belgium and Luxembourg, preventing American armor from sealing off German penetrations before Panzer spearheads could reach their objectives along the Meuse River. German planners calculated that concentrated Panzer attacks would eliminate American tank units piecemeal during the offensive's first days, destroying enough American armor that surviving units would be unable to mount effective counterattacks. These calculations assumed that 60 to 80% of American tanks suffering penetrations would burn and become total losses. This assumption, accurate for 1943 but completely obsolete by December 1944, led German planners to systematically underestimate American regenerative capacity and overestimate how quickly American armored strength would collapse under pressure. SS Obersturmbannführer Joachim Paper's Kampfgruppe, spearheading 1st SS Panzer Division's attack, encountered this new reality near Stoumont on December 19th. His Panthers and Tigers achieved numerous penetrations on Shermans from the 740th Tank Battalion at close range during fierce fighting in the village. Yet American resistance continued with unexpected tenacity. Tanks that should have burned after taking hits instead withdrew to covered positions, continued fighting with damaged but functional main guns, or simply buttoned up and reversed out of the engagement area under their own power. In post-war interrogations, Paper expressed particular frustration at American tanks continuing to fight after taking hits that should have destroyed them. He attributed this to American industrial capacity providing unlimited replacement vehicles, never recognizing that many tanks he believed destroyed were actually the same vehicles repaired and returned to combat. The 740th Tank Battalion's maintenance section, working in a commandeered barn 3 miles behind Stoumont, repaired and returned to service 11 tanks during the battle's 6 days, tanks that Piper's after-action report listed as confirmed kills. The 761st Tank Battalion, the African-American Black Panthers, demonstrated wet-stowage advantages throughout their 183 days of continuous combat from November 1944 through May 1945, including heavy fighting during the Ardennes campaign. Staff Sergeant Reuben Rivers, posthumously awarded the Medal of Honor for actions in November 1944, exemplified the survivability wet stowage provided. His tank absorbed 2 direct hits on November 19th that penetrated the hull but failed to ignite ammunition. Rivers continued fighting despite serious wounds, his crew surviving hits that would have killed them all in earlier Sherman models. When Rivers was finally killed by a 3rd penetration that struck him directly, his crew was able to bail out through a fighting compartment that wasn't burning, recovering their commander's body rather than abandoning him in a flaming wreck. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.